Hi there. I want to give a little more context as to why we do the electron configurations while I go through a couple more examples on your practice worksheet. The answer key will also be posted. The key to getting a good start is counting our electrons. So for iron, it looks like number 26, it's top middle of the transition metals. And if we're going to use the periodic table to guide us for the electron configuration, we have to see that argon is the noble gas that comes before iron. So again, I'm going to start with argon, and it's 18 electrons. And if I look at my periodic table, the next section of the periodic table, it looks like potassium and calcium, which is the fourth row down. So that means it is the fourth energy level. So we get 4, and then the first two columns are S block. So we get 4s2, and then remember, the next section is 3d. So we have a little bit of a different order. It goes 4s2 and then 3d. And it looks like if we count 1, 2, 3, 4, 5, 6, iron has 26 electrons, so it's the sixth one here. And we get argon 4s2 3d6. And a lot of students make a mistake by saying that there are 6 or 8 valence electrons here, but our highest energy level is 4. There is a 4p orbital, it's just empty. So our fourth level s and p electrons are 4s2 and 4p0, so there are 2 valence electrons. If we fill in the orbital diagram for this one, we could leave off the argon and just go with our outer electrons. So sort of like the previous example, we'll have the 4s, and then the 3d is a set of 5 orbitals. If we put in our arrows, there are 2 electrons in the 4s, and then because of Hund's rule, we do 1 arrow at a time. You usually start with an up arrow, but doesn't matter. And we're going to box only the 4s electrons. So iron and most transition metals, by the way, have 2 valence electrons. One reason we're doing this to find the valence electrons is you might have heard of the magic number 8 before, that metals tend to lose electrons so that they empty out their valence electrons. So iron becomes a +2 ion because when it reacts with a nonmetal, it's going to lose those 2 electrons. So iron typically becomes a +2. And with that same logic, if we were looking at arsenic, well, arsenic has 5 electrons, so arsenic can pick up 3 electrons and become a 3 negative charge. So metals tend to lose electrons so that they empty out their valence electrons, and nonmetals tend to gain electrons in order to fill up. There is going to be some sharing that we talk about later, but to kind of see where we're going, if I took iron and arsenic and put them into a compound, it ends up being a neutral compound if we have 3 iron plus 2 ions, or what we call the iron 2 ions. If we have 3 of these guys and 2 arsenic ions, looks like we have a +6 and a -6. So our formula, and again, this is getting ahead a little bit, but our formula would be 3 irons and 2 arsenics. So this would be a compound called iron 2 arsenide. Again, that's getting ahead a little bit, but one reason we want to get these valence electrons right is so we can predict what charge metals and nonmetals will take when they become ionic compounds. A little bit of one other thing that we can tell from the electron configuration in the orbital diagram is something about magnetism. So we have 3 kinds of magnetism. There is ferromagnetism, there is diamagnetism, and there is paramagnetism. So a question you might be asked is, are there unpaired electrons? And if we look at the example of iron, there are clearly some unpaired electrons. In fact, there are 1, 2, 3, 4 unpaired electrons. And if you have any unpaired electrons, we say that it is paramagnetic. And the only other thing that you would be asked is, well, if there are no unpaired electrons, then what kind of magnet is it? It would be diamagnetic. So if all of your electrons are paired, we say it is diamagnetic. If there are any unpaired electrons, we say it's paramagnetic. So I'll put a P or a para right here. And then ferromagnetic's a little bit different. It's a permanent magnet, and I will save that discussion for later. But see if you can think of an element or write out an element that is diamagnetic. So no unpaired, or all paired electrons, no unpaired electrons. Perspective. Let's do one more example. Show my periodic table down here. And platinum is way down here at number 78. It gets a little tricky here because it involves the F sublevel. So for platinum, we want to make sure that with its 78 electrons, we get that part right. And the noble gas that comes before platinum is xenon. So we will write xenon right here. And that takes care of 54 electrons. After xenon, it looks like we're going to go to the 6s2. After 6s, there's actually an insert here on the periodic table where this entire 57 to 71 is the F block. There are 14 elements there because of those 7 orbitals. So we're actually going to go to 4f14. And then if we count along after that, so we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then for some reason this periodic table puts Lu right here. In other periodic tables it's shown on the main transition block. So we get 1, 2, 3, 4, 5, 6, 7, 8. And that would give us 5D8. And if you're wondering how I knew it was 5D, is because the D block starts with 3D, 4D, and then 5D down here. So just to double check and count our electrons, xenon has 54. And then if we add up the electrons for the other outer shell, we get 2 plus 14 plus 8, which gives me another 24. And that's 78 electrons. Perfect. How many valence electrons does platinum have? Just like before, I won't show the arrows for this one, but the highest energy level is 6, and the s orbital has 2. The 6p doesn't have any electrons in it. I hope that helps, and shoot me an email if you have any questions.